Welcome to Episode 4, Advanced Math Topics Continued. In the last class, we introduced quadratics, polynomials, how to factor to solve quadratics, how to complete the squares and derive the quadratic formula. In this class, we'll finish that off and add a little graphing features, and we'll begin with special factoring cases. These are particular cases of factoring that will appear over and over on the exam. The first one is the difference of two squares. We saw a little bit of both of these in the last class. Now let's really dig into them a little further. Note the difference of two squares says if I have two things squared, x squared minus y squared, that equals the product of what we call the conjugates. That is the things that are being squared. So x squared, it's x being squared. Y squared is y being squared. So x plus y times x minus y, those conjugates form the difference of two squares. The key here is the xy terms in between cancel out. So how do we see that in practice? Well, usually it's dressed up in some form or fashion, kind of like the expression shown here in pink. 9x to the fourth is actually 3x squared squared. And 49 fourths times x plus 1 to the sixth is really 7 halves x plus 1 cubed, that whole thing squared. So this equivalent expression written out as a difference of two squares, we can write them in terms of the conjugates, the things being squared. Now they may not look as simple as x plus y, x minus y, but they really are. It's 3x squared that's being squared. I'm going to add that to the 7 halves x plus 1 quantity cubed. That is essentially my x plus y. And I multiply that by 3x squared, the first thing being squared, minus the second thing being squared, 7 halves times quantity x plus 1 being cubed. That is the breakout into the two conjugates, x plus y times x minus y. A bit messier and complicated, but it is a difference of two squares and can be factored as such. We also use difference of two squares to factor and cancel or simplify in many cases. For example, x squared minus y squared over x plus y actually equals, and I think we saw this once before already, x plus y times x minus y, the product of the conjugates, and my denominator was itself a binomial x plus y, which is equivalent to the binomial on top. That cancels. It simplifies to x minus y. Take advantage of that simplification when you can see chances to factor the difference of two squares. The second special factoring case we'll run into is perfect squares. We saw this a little bit as well. When I take a plus b and I square it, do not, and I repeat, do not think that's a squared plus b squared, a very typical algebra mistake. I think most of you probably know that by now. The perfect square case is a plus b. When that's quantity squared, we would FOIL it out. It's essentially a plus b times a plus b. There's a real quick trick to do that faster. I simply take the first term, a, I square it. I double the product of the two terms, ab, 2ab, and I take the second term and I square that, and that's my perfect square. And I like to think of it that way because when I identify perfect squares, I'm often looking for terms that are squared on both ends, and I check if the intermediate term is double the product of the two things being squared. Note we used this particular perfect square format to complete the squares, so you want to get to know it and be able to recognize it. So some fairly typical examples you want to know is x plus 1 squared is x squared plus 2x plus 1. X plus 2 squared is x squared plus 4x plus 4. X plus 3 squared equals x squared plus 6x plus 9. These are just some very typical examples, so you're used to seeing them and seeing the coefficients and numbers associated with them, so you can detect them and answer the questions pretty quickly. Also, you want to be aware of when they're dressed up, like the difference of two squares in pink, and be able to identify that. In addition, there are a couple other quick tricks you might want to know to help you calculate things more quickly. Two of them are the sum of the roots and the product of the roots. And questions will ask for these, so it can help you out from time to time. The sum of the roots, assuming I start with a quadratic in standard form, is simply going to be minus b over a. It's worth memorizing. So one way to solve this problem would be to figure out the roots, solve the whole problem, and then add those roots together. But if we remember our quadratic formula, essentially when we add together the plus and minus cases, my first root and my second root, the plus minuses cancel, and I end up doubling minus b over 2a, which when I double it, the 2's cancel, and I get minus b over a. So really quickly, when I see a standard form quadratic, for example, x squared minus 5x plus 6, we know that factors into x minus 3, x minus 2. The roots there are plus 3 and plus 2. The sum of those roots would therefore be 5. Well, let's see if our method works here real quick on that. Minus b would be minus 5 over a, which is 1, not shown, but the leading coefficient is 1. And sure enough, it's 5. It's the very same answer I would get if I actually solved the problem. In a lot of more complicated cases, especially when I have irrational roots, this is a simple way to get the sum of the roots. The product of the roots might even be easier. It's simply c over a. So when I multiply out those roots, the first solution times the second solution from the quadratic, I'm going to get c over a. How do I know I'm going to get that? Well, if you think about it, my quadratic, again, is essentially a first term plus or minus a second term. When I multiply out the plus and minus case, I'm essentially taking a difference of 2 squares, which means my intermediate square root terms, the radicals, that ugly discriminant, cancels out, and I simply get c over a. Well, let's check if that works as well. Let's go back to our x squared minus 5x plus 6 quadratic, which we know what the roots are. The product of those roots will be 3 times 2. It should be 6. Does it work out if I plug in c over a? Well, let's think about it. C is plus 6. A, as we know, is 1, the leading coefficient of the x squared. Sure enough, the answer is 6. A quick way to find the product of the roots is to calculate c over a. In the last class, we learned about the discriminant test, which told us whether we had 0, 1, or 2 real roots for any degree 2 polynomial or quadratic. We saw if the discriminant b squared minus 4ac was greater than 0, we had 2 real roots, that is 2 intersections of the x-axis as shown there. If that discriminant value equaled 0, we only had 1 intersection of the parabola with the x-axis. It doesn't matter if it was upward facing or downward facing, just 1 intersection, never crossed over the x-axis. If our discriminant was less than 0, we know we had no real roots, and graphically that meant we did not intersect with the x-axis. We either floated above it, below it. So let's extend this concept and learn more about graphing given the different formats of quadratic equations. We'll start with the standard form. What can we determine and graph directly from the standard form? Note, by the way, everything we've done on finding roots and x-intercepts, they've all just been about that. It's not included the other factors I need to graph. I want to know what the y-intercept is. I do want to know what the x-intercepts are, but I also want to know the shape and direction of my parabola. Am I opening upward, downward, narrow, wide? And I want to know where my vertex is. What's the minimum and the maximum point of the graph? These are all aspects of graphing. We've really been focusing on only the x-intercept up to this point. So let's learn about the other features. In standard form, my c value is the y-intercept. This is where my graph will intersect the y-axis at x equals 0. And you could plug x equals 0 into the function, you'll get y equals c. So given to you as a constant directly in standard form is your y-intercept. What else do we know from standard form? Well, we can actually do some work to figure out the vertex. The vertex, if we called that h comma k for that vertex point, which is the minimum or maximum point that lies on the axis of symmetry, that midpoint of the parabola, we know the h value, that is the x value of that vertex, is minus b over 2a. It's that first term of the quadratic equation. So I can use that to figure out my vertex h value. I then plug that h value into the function itself to get the y value, the k value as we would call it. And then I can figure out h comma k. By the way, that's a quick way to convert a standard form equation to a vertex form equation as well. So these are the things I can figure out quickly and know directly from the information given to me in standard form. The b value, note, that has an effect on the graphing if we think about it. If b is 0, like y equals x squared, c value there is 0 as well, which is why we intersect at the origin, but it's symmetrical around the y-axis, because if I find h, it's minus b, which is 0, on y equals x squared. There's no b term, which means h is 0, and the y-axis is my axis of symmetry. When the b value is not 0, that's when my parabola will shift right and left. And standard form is not the best graphing form because it could go up and down as well. We don't know exactly how it shifts, but we know it will shift off the y-axis. So you can keep that in mind if you're working from a graph and trying to figure out standard form as well. Okay, what about an intercept or factored form quadratic? What do I know directly, and what do I have to do to figure out the other factors of graphing, like the y-intercept, the a, the shape and direction of the graph, the vertex, etc.? Well, right away I know the m values, the factors, those constants directly tell me what the roots of the quadratic are. So it might be something like this. That would be m and n. Those would be my intercepts on the x-axis. So directly given to me in factored form is my x-intercept. The a, well, that will be the same a as my standard form. If it's positive, I'll open upward. Negative, I'll open downward. And what else can I figure out? Do I know my y-intercept? Not easily or directly from factored form. I could multiply it out into standard form and then figure out what my c value is. So that's one way I could get the y-intercept from factored form. How about my vertex? Well, my vertex in standard form I found from h equals minus b over 2a. In factored form, it's almost even easier. All I have to do is take the average of my roots. It's going to be m plus n divided by 2, because I know that average is the midpoint of the parabola. It lies on the axis of symmetry, and that's where the h value of my vertex lies. Again, I would plug in that h value back in to get the k value for the min-max point. Let's see that with an example and see how it works on standard form and factored form. Suppose I was working with, keep it simple, y equals x squared plus 5x plus 6. Well, we know that factors to y equals x plus 3 times x plus 2. So from the standard form, I could figure out h equals opposite of b, which is opposite of 5, over 2 times 1. It's opposite of 5 halves. Okay? And then I could plug that back in to figure out what my k value will be. In the factored form, I would take the average of the roots, which are, in this case, minus 3 for the x plus 3 factor, and x equals minus 2 for the x plus 2 factor. That average is minus 3 plus minus 2 divided by 2, also minus 5 halves. The same h value as I would have determined if I had the same standard form equation. So that's how I would do it in factored form. Almost easier. How would I find the k? Well, I'm going to plug that value back in. In many cases, plugging back into the factored form is even easier, because notice minus 5.5. That's minus 2.5. So minus 2.5 plus 3 is going to be a half, and then minus 2.5 plus 2 is going to be minus a half. So you end up getting the negative square of whatever that difference is, which is minus 1/2 squared, or the answer is minus 1/4. That's the minimum point of my quadratic or my parabola. And HK is minus 5/2, comma, minus 1/4. So what does the graph actually look like for this particular quadratic? We know at minus 2.5, I've got my axis of symmetry. At minus 3 and minus 2, I've got my x-intercepts, or my zeros. And I know my graph is going to go down. It's pretty shallow. It's going to go down only to a level of minus 1/4. That vertex point will be minus 5/2, comma, minus 1/4. And again, if I want that y-intercept, it's easier had from the standard form where it's directly given to me. It's going to be +6. And that's how I go about graphing it. My a value on each of these is 1, so it has the same shape and it opens upward, just like the y equals x squared, the most simple case parabola, if we want to think of it that way. The vertex form might be the most analogous to y equals mx plus b. It's the most logical graphing format among the quadratic forms. It basically says y equals a, the same a that denotes our shape and direction of the parabola, times quantity x minus h squared plus k. Note that h is your constant, that's the x value of the vertex, and k is the y value of the vertex. So h comma k is the constants that represent the vertex or the min-max point. Again, questions will ask about that, and that's what you can get directly in vertex form. So if they wanted an equivalent quadratic where the min-max point is given as a constant, you would want to deliver a vertex form equation, not a standard or intercept form equation. Okay, so how would we work with this? How exactly does it go? Let's go back to our particular example of y equals x squared plus 5x plus 6, and figure out how would I get my vertex form and graph that, for example. Well, one way to do it would be to complete the squares. That's the more formal approach. But I'm not going to take that time. I'm going to use the quick way I would probably use on the exam. I'd quickly know from my standard form h equals opposite b over 2a, which in this case we already said is minus 5/2. And then I could figure out my k value by plugging back into my factored or standard form, which we know in this case was minus 1/4. So in vertex form, that same equation would be y equals 1, that's my leading coefficient, x minus or minus 5/2 quantity squared minus 1/4, that is plus negative 1/4. So let's just simplify that a little bit. Y equals minus in parentheses is plus, so y equals x plus 5/2 squared minus 1/4. It's worth noting the plus symbol as an offset to x means the actual value of h will be a negative 5/2 value. That's how we get the plus. It's a minus. So keep that in mind. That might be important for avoiding sign errors and getting the right answer, because they will show those different options in the answer choices. So again, how does this look in graphing? Well, it's pretty easy to graph in some senses because my vertex points are given to me. At minus 5/2 minus 1/4, I have my vertex, which we saw before because we already found it from the other forms. And I know my shape is going to go 1 over 1 squared up, 2 over 2 squared up. It's going to look like the y equals x squared parabola opening upward. And what I don't get from this graphically are my zeros and my y-intercept. I don't get those directly. So if I started with my vertex form equation, how would I find my zeros and my y-intercept? Well, one thing I could do to get it back to standard form, where I have c value is my y-intercept, I would just multiply this out. So that's one option for the y-intercept. If I wanted the zeros, Well, again, I could multiply it out and then factor it and figure out what the zeros are. Okay, and that would work, and a lot of students do it, but boy, that's the equivalent of climbing up and over a large wall when you can simply walk around it. Here's how you would really do it. Remember, if I want the y-intercept, I simply set x equal to 0. So let's do that in our equation. Y equals 0 plus 5/2 squared minus 1/4. Y equals 5/2 squared is 25/4 minus 1/4 equals 24/4, which equals 6. The y-intercept is 6. We already knew that's the case, but see how much easier that is? Okay, well, what about the zeros? How about those? All we need to do is set y equal to 0 in our equation. So 0 for y up above equals x plus 5/2 squared minus 1/4. Okay, this looks like it might be a little more complicated, but not really. We already kind of have the perfect square set up. We've almost completed the squares. We completed completing the squares. So all I'm going to do is add 1/4 to the other side, and I'm going to switch the sides here. X plus 5/2 squared equals 1/4. And what would I do then? Well, I'm going to take the square root of both sides once I've isolated my squares on the left. And what do I get as a result? X plus 5/2 equals plus or minus the square root of 1/4 is 1/2. And I'm going to take my 5/2 to the other side. X equals minus 5/2 plus or minus 1/2, which has two solutions. Minus 5/2 minus the half is minus 6/2, or x equals minus 3. And minus 5/2 plus a half is minus 4/2. X equals minus 2. These same roots or zeros we got before. So really, you don't get this information directly from vertex form graphs, but you can access it easier than you think. So note, I have to be able to go back and forth between standard form, my factored form, and my vertex form pretty easily. As a quick review, from factored or vertex form to standard, I just multiply everything out and distribute. If I want to go from standard form to factored form, well, that's all the effort we spent on factoring. That's how you do it. If I want to go from standard form to vertex form, I usually use my h is equal to minus b over 2a and then plug back in to get k. That's easier and generally faster than completing the squares, I find. If given a graph, how do I find that a value that denotes the shape and the direction of the graph? Well, if it's plus or minus, I know the direction, opening upward or downward respectively, but how do I get the shape, the narrowness or width of my parabola? Well, I use a couple approaches here. One, I know our general equation in simplest form for a quadratic is y equals x squared. It is by definition a degree 2 or a squared function. So essentially, if I shift over plus or minus 1 on x squared, my y goes up, always positive when I square, even a negative, up 1 squared. So it goes up 1. If I go left or right, plus or minus 2, my y value goes up the square of that, which is plus 4. And then if I shifted 3 in x off the vertex of my parabola in the x direction, left or right, I'm going to go up 9. That's equivalent to an a value equal to 1. It's going up 1 times x squared. So I can actually utilize that in this case. Let's see the graph where I've got a vertex 4, negative 4, and I have zeros at 6 and 2. How does that work? Well, if I go from 4 to 5 over 1, I go up 1 squared. If I go over 1 more to 6, I go up 2 squared, which is 1, 2, 3, 4. I go up a total of 4 for going over 2. So now I know the value of my a in this graph is going to be a equals 1, and I can appropriately set my vertex form in the equation. It would be y equals x minus the h is 4 squared plus k, which is minus 4. And my a value equals 1. I don't need to write it, but I'll put it in there just to show it. And I have the equation of my vertex form. The other method, which might be the more formal approach, is to do something as follows. If I know my vertex point, I only need another point to get the equation of a parabola. In standard form, that's not true. Like a line, you need 2 points to get the equation of a line. If I have a parabola, I would generally, in standard form, need 3 points because I could have that parabola going through it, I could have that parabola going through it, I could have that more extreme parabola going through it. Well, I missed the point, but you get the idea, hopefully. I need a third point, say there, to figure out, in fact, that the correct parabola is this one, definitively, not the other ones. Well, if I have the vertex point, this is a special case, because then I only need one other point. And I have that other point with my zeros. I could use, say, for example, 6, 0. Now I could plug back into my vertex formula. Generally, I would say my y value equals a times x minus h, which is x minus 4 squared plus negative 4, which is just minus 4. Now, I need to find a, but I have my second xy point, 6, 0. So I know 0 for y equals a times 6 for x minus 4 squared minus 4. 6 minus 4 is 2 squared, so 0 equals 4a minus 4. 4a equals 4. A equals 1, the exact same answer. And again, I have the equation of my vertex form equation. Y equals 1 times x minus 4 squared minus 4. The exact same equation I got up here from estimating the offsets from my vertex point and knowing how quickly the graph goes up. Let's look at the example again in orange here. If I have at least half my parabola to the left and I move left 1, I'm going to go up 1 squared based on y equals x squared format. But actually, the graph goes up 2, which means it's going up 2, the a constant, times 1. So it looks like, in this case, a equals 2. Let's check that if I go over 2 to the left. Now I should go up 2 squared, which would normally be 4, but it actually looks like on this graph, it's 8. Well, 2 times the normal x squared for the 2 offset would be 4. I'm doubling that. It's 8. So again, it looks like my a equals 2. So for this graph, I can quickly determine a equals 2. I simply take the offset of x, square it. That should be my change for y if a equals 1. And whatever multiple it actually is of that on the graph, that is what my a value is. Another way to look at it, I find it faster than plugging in individual points, but entirely up to you, whatever you're comfortable with. In either case, know how to calculate the value of a. Let's explore the relationship between roots and graphing a little bit further. So assume, for example, I had the following graph where I have the various zeros, minus 5, minus 1, and 6 shown. What would be a possible set of factors for this particular polynomial? Well, in this case, we pass through minus 5. So that corresponds to the factor x plus 5. Don't forget to change the sign there. We pass through 6, so that corresponds to the factor x minus 6. And then we pass through negative 1. Well, wait a second. We don't actually cross the x-axis there. So if we recall, anytime we come down to touch the x-axis and return, that's a squared factor. So x, the opposite sign, x plus 1 squared. You might see an answer that's x plus 5, x minus 6 times x plus 1. That is actually the wrong answer. When we have this situation where we touch the x-axis and return, it's a squared factor for the x plus 1. So a possible factor set for this function would be x plus 5, x minus 6 times x plus 1 squared. Be careful and be aware of that squared factor case. How do we think about and go about solving cases where we have lines and nonlinear functions? For example, here we have what is essentially a parabola, and a line. What might that look like? Well, again, in general, I have a parabola and a line. There could be no intersections, 0 real roots. The line could be tangent to the parabola, have 1 intersection or 1 real root, or it could cross through the parabola in 2 different places. Just like our quadratic, we have 0, 1, or 2 real roots. If we solve this by substitution, we'll effectively get an equation that becomes a quadratic. X squared equals x plus 1. 0 equals x squared minus x minus 1. We're effectively solving a quadratic, which means we'll get 0, 1, or 2 real roots. We'll essentially have a new quadratic to solve as a result of this combination of parabola and line. Okay, what about the case where we have x squared plus y squared? That's the graph of a circle, and y equals x is, of course, a line. How does that work out? Well, again, I could have the circle independent of the line and have 0 real roots. My line could be tangent to the circle, have 1 real root, or my line could pass through the circle in 2 different points, have 2 real roots. Again, this is the outcome of a quadratic. And if we solved by substitution, we would realize we end up getting a quadratic again, and we could solve to have 0, 1, or 2 real roots for the new quadratic that I obtained by substitution. So keep that in mind. That's how we would get results for parabolas and lines, circle and lines, typical situations we'll run into on the exam. It helps to understand the parent-child relationship between graphs and utilize the offsets to the x and y to figure out exactly what you're graphing and figure it out pretty quickly. So I'm going to start with the vertex form of our quadratic to highlight this. Essentially, we know this is a quadratic whose vertex is at x minus 2, indicates the h value is 2, and plus 5 indicates the k value equals 5. I could rearrange the 5 to the other sides and say this is essentially y minus k, the offset to the y, and x minus 2 is the offset to the x. This is a child graph whose parent is effectively y equals x squared. I know what y equals x squared looks like. Y equals x squared is our basic parabola that goes through the origin, and the k and the h offset adjust this graph. So x minus 2 is an offset 2 to the right. All else equal, this graph would move over 2 to the right for the offset to the x. X minus 2 indicates my vertex moves to 2, 0 from 0, 0, the origin. The plus 5 indicates it shifts upward 5. Or alternatively, I can think of that as the offset to y, y minus 5, indicates the upward shift, positive 5 direction. Notice it's defined as y minus k offset. So this is very typical of any function. I don't care if it's a square function, if it's a line, if it's a sine function, or otherwise. I have offsets to x and offsets to y that will shift my graph around. Let's try the example of y equals the square root of x minus 1. How does that change? Well, a square root of x graph we've seen before looks something like this. If I'm offsetting the x by minus 1, that means I'm shifting the graph 1 to the right, and it will look effectively like that. Almost essentially the same graph, but shifted plus 1 to the right for my x minus 1 offset. Likewise, if my parent graph is y equals 2 to the x, that's going to look something like 2 to the 0 power would be 1. And as x goes negative, that becomes 1/2, 1/4. It approaches 0. And then as x goes positive, it moves up exponentially as a growth function. So what then would the graph of y equals 2 to the x plus 2 be? Well, the x plus 2 is an offset of minus 2, that is x minus minus 2. So it shifts this same graph 2 to the left. every point on my new graph, all else equal, will be 2 to the left. But I also have my plus 2, which means every point is also shifted up 2 on my graph as well. So I take every given point and I shift 2 to the left for x plus 2, and the plus 2 is a direct addition to y, which is up 2, and the green line would become my new graph. So in this way, I can use my offsets to the parent function to figure out what my new graphs will be. And we run into this time to time from graphing on the exam. So it's good to be aware of the parent-child relationships and how to adjust for them. Those parent-child relationships are essentially function independent. I don't care if it's square, square root, whatever the function may be. The x minus h offset means shift that graph h to the right. The plus k means shift that graph up k vertically. Okay, one more thing I want to point out relative to this is in our quadratics, y equals x squared passes through the origin. This might be 5 here. That graph would be y equals x minus 5 squared. It's just a shift to the right. This graph would just be, call this minus 5, y equals x plus 5 squared. The plus 5 indicates the shift to the left because that's minus minus 5. Always be careful of the signs. In each of these cases, there is one intersection with the x-axis. All of these quadratics or parabolas represent perfect squares of binomials. We mentioned that earlier in the class without really explaining it. But if this is true, you always have, for a perfect square, one intersection, or likewise, if I have one intersection from my discriminant test or just visualizing it in a graph, I know I'm looking at a perfect square quadratic. Okay, finally, we get to look at nonlinear functions or equations beyond just quadratics. Let's look at radical equations, equations with square roots in them. In most cases for the exam, we're either going to intuit the answer or plug in the answer choices rather than go through the formal solution, which usually entails isolating your radical function, squaring both sides to undo the square root, and then solving, which unfortunately gives rise to possible extraneous solutions that do not work in the original equation. Let's take a look at these scenarios and understand it better. So suppose I started with square root of x plus 4 equals 4. Well, this I can realize that 4 is the square root of 16. So I need my x plus 4 to be the same thing as 16, and I can set up that equation and solve. X equals 12. I can see that 12 plus 4 makes the square root of 16 or 4. It's easier to intuit that than try to square both sides and work from there. More typically on the exam, if I have the square root of x plus 2 plus 4 equals x, I could go through my formal solution. I would isolate my radical, x plus 2, square root, equals x minus 4. I'm going to square both sides to get rid of my radical, and I'll end up with x plus 2 on the left, and that equals x minus 4 squared, which is x squared, minus 8x, double the product of the two, and square the last one, plus 16. I'm going to combine all these terms on one side to set my polynomial equal to 0, which is how we solve for the roots. So x squared minus 8x minus x would be minus 9x. 16 minus 2 would be plus 14. And I can factor this simple case. It's simply going to be x minus 7 times x minus 2 equals 0. That means x equals 7 and x equals 2 are the roots. That's what I get from my formal solution. Note, almost always in the answer choices, we see those roots there already with a third number, oftentimes a 0. That is almost never the right answer. So why did I do all that work? Because now that I've done that, I still have to plug these results back into my original equation to see if they work. So let's try that over here. Square root of 7 plus 2 plus 4 is the square root of 9 plus 4, which is 3 plus 4, and that equals my answer, x, 7. Yes, it does. That checks. X equals 7 is a valid solution to this equation. But what if I checked 2? Square root of 2 plus 2 plus 4 is the square root of 4, or 2 plus 4. Does that equal x, which is 2 on the other side? It does not. 6 does not equal 2. X equals 2 is not a valid solution. What did I just do? I actually took my answers from my formal solution and plugged them back in. Well, why didn't I realize that from the beginning? Avoid the solution entirely and just start plugging in my answers, knowing 0 is not likely to be correct. Plug in 2, realize that doesn't work, so therefore it can't be 2, 7. And if I wanted to plug in 0, I quickly see that doesn't work. And I immediately get the answer is correct when I plug in 7. No need for all that extra work. So you could do the formal solution for most radical equations, but in most cases on the exam, when it's multiple choice, you don't need to. You can just take your answer choices and plug them back in. So you should know how to solve them formally, but again, also know how to work them more effectively on the exam. Let's talk about circle equations. They're not functions, but there are equations that define circles regardless. For example, x squared plus y squared equals 1. And that defines my green circle with the center at the origin and radius 1. Oh, that circle's too pretty. I like my terrible hand-drawn graphics. They're so much more fun. Well, anyway, how do I expand this idea to a more general circle equation? Well, the answer is we know how our parent-child graph relations work. X minus h squared plus y minus k squared, where h and k are the respective offsets to x and y, equals the radius squared. What does that mean? That means, in general, the center of my circle will move from 0, 0 to h, comma, k. That would be the new center of my circle. And 1, well, it wouldn't just be radius 1. It actually would be radius squared 1. The numerical value is the radius squared. So r represents the radius of the circle. The equation presents the radius squared. So, okay, that's fine and wonderful. Let's try an example. What if I had x minus 2 squared plus y plus 2 squared equals 4? What circle would that be? Well, the center of my circle would move 2 to the right for the minus 2. So my center would move to 1, 2. And it would move 2 down for the offset plus 2 for the y, because that's essentially y minus minus 2. So I'd go 1, 2, down. This would be the new center of my circle. The radius squared of my circle would be 4, which means the radius of my circle is 2. So it would look something like that. And now that's a really poorly drawn hand circle. I love it. So now my center of my circle for x minus 2 squared plus y plus 2 squared is 2, comma, negative 2, and it has a radius equal to 2. And that would be the new graph of my circle. We can see that parent-child offset relation working for the function that is the circle equation. Oops, did I say function? Circles aren't functions. Okay, that's fine and well, but what would we do if we saw the following equation? X squared plus 2x minus 6y plus y squared equals 3. What would you do? Hopefully your answer is not, I would panic. This is a long equation with two variables. In fact, it's what we would call a long form circle equation. A little different than our standard form circle equation, which, as we saw last time, was our x minus h squared plus y minus k squared equals the radius squared, where hk was the center of the circle and r is the radius of the circle. Well, suppose I was given this equation and asked what is the center of the circle or what is the radius of the circle. Well, my objective would be to take this long form and put it into standard form. Then I could easily detect what the answer would be for the center or the radius. Okay, well, how am I going to go about doing that? Well, here's one case you really want to learn how to complete the squares. Because what does this really look like? This and this look like standard form quadratics in x's and y's, sort of. And this look like perfect squares in x's and y's. And one way to get from the standard to the perfect square or vertex form is to complete the squares. So that's exactly what I'm going to do. I'm going to create a perfect square on my x's by adding some amount that makes that standard form a perfect square. And likewise, I'm going to complete the squares on the y's. I'm just going to rearrange it a little here to put it in standard form and add some unknown amount that will make that a perfect square. So my objective is for that to be a perfect square and that to be a perfect square when I complete the squares. And then I'll get 3 plus, well, I would have to add to the right side whatever I added to the left side as well. Okay? So what would these numbers be? Let's go ahead and complete the squares here. I would have my coefficient of the x, the 2, and that becomes 1. That's my perfect square for x's, x plus 1 squared. If I want to fill in the amount, I need to square that value to create a perfect square. 1 squared is just 1. Okay? So I need to add 1 over here on the right side as well. All right, let's complete the squares on the y's. Minus 6y, I'm going to have that coefficient of the y. That's minus 3. So y minus 3 will be my perfect square in the y's. Well, what do I put in the missing amount box that makes that a perfect y minus 3 squared? Well, I have to square the minus 3, which is going to be plus 9. So I have to add 9 here as well. So x plus 1 squared plus y minus 3 squared equals 3 plus 1 plus 9 is 13. So what do I know about this circle now? I know the answer to the question. My center of the circle, h comma k, is going to be x plus 1 indicates h is negative 1, and y minus 3 indicates k is plus 3. Don't forget that sign change. That's very important. We saw that in our quadratics. You have to be careful of it in circle equations as well. See how many opportunities there are for sign mistakes? Always be careful. My radius here is not 13. Be careful of answers that show that. R squared is 13, which means my radius is the square root of 13. And whichever they ask, I can answer. And that's how we convert long-form circle equations into standard form circle equations. Okay, let's look at exponential growth and decay functions. They essentially denote fractional or percentage changes from the current period amount. They are not a constant rate of change. Any problem that denotes a constant rate of change is a linear function. So what does the graph of an exponential or growth decay function look like? If it's a growth function, it might start at some value, go up almost linearly, and then begin to hockey stick upward on a curved basis. If it's a decay function, it might look like it's starting at some point and go down and begin to decay very rapidly and level off as we get lower and lower. This is essentially a decay curve, and this is a growth curve. In either case, they are exponential functions defined by the following function: y equals AO r to the x. And what do these components mean in this function? Well, y is your y value. X is obviously your x value on the curve, on the axes. AO denotes your initial amount. That is the amount of money, the amount of bacteria, whatever that initial amount might be at x equals 0. R is our constant multiplier. This is an important one to note. Students mess up the calculation of R frequently. What is R? Suppose I had a percentage change that was an increase of 10% every year from the previous amount. That would be an exponential function. What is my R? It's always 100% plus the percentage change, which in this case is plus 10%. And we express that as a decimal. So R equals 100% plus 10%. As decimal, that's 1.1. Do not think R equals 0.1. That makes no sense if you think about it, because if you multiply 0.1 times, say, $100 in the previous term's bank account, if that's what it represented, you'd get $10 the next period. $10 is not a 10% change. It's a 90% change from $100. So remember, you're always adding the percentage change to 100% and expressing that as a decimal to get your multiplying factor there. And by the way, if it were decay, that factor would be less than 100%. You'd be losing money. So let's suppose I had 20% decline in the amount of the drugs in my system or something like that, whatever it might be. So R in that case would be 100% minus 20% of the medicine that decays or gets flushed out of my body every period equals a multiplicative factor, a constant multiplier of 0.8. That represents a 20% decline per period. So make sure you know how to calculate R and get it right. Let's see how this works in action in a couple cases. Suppose I had 1.0 million people in a city in year one, and every year the city population grows 2%. What would my constant multiplier be? In this case, it would be 100% plus 2% in decimal form. R equals 1.02. So my exponential equation here, which would be a growth curve, equals y equals AO is 1.0 times my multiplier 1.02 raised to the x. What would that curve look like? Well, that means when x equals 0, my function value would be 1.0 times 1.02 to the 0. Anything to the 0 power is 1, which means I'm multiplying 1 times my AO, my original amount. My intercept is going to occur at 1.0 million people. And I'm going to increase very slowly, but eventually it's going to curve upward in my growth function. And that's what the graph of that particular function will look like. What if it were a decay function? Suppose I had y equals, and I lost 10% per period in my stock for 3 periods. What would that look like? Suppose my initial price of the stock was $50. My AO, my original amount, would be 50. My loss of 10% would be 100% minus 10%. In decimal form, that would be a constant multiplier of 0.9, 1 minus the 0.10. And over 3 periods, x would be 3. That would be the value of my stock after 3 periods on a decay function. So at time 0, again, it would be 50 times 0.9 to the 0. 0.9 to the 0 is 1. So 50 would be the original price, and then it would decay down each period until year 3. It would be exactly that value, 50 times 0.9 cubed, which, by the way, is roughly going to be about 36, if we're to estimate that. There are a couple intricacies you want to know about this. Let's suppose the value of my investment equaled the original amount times my multiplier to t number of years. And that would be the function for the value of my investment. And let's say R was, about 12% increase annually. And we could say A, my original amount, equaled 1,000. So my value of my investment would be 1,000 times 1.12 for the plus 12% increase. My factor would be 1.12. I multiply that by my previous period to get the new period to the t. And the question asks, what's the equivalent value based on m, where m equals the number of months rather than the number of years? What would that function look like? Well, some students might say, oh, 1.12, 12% is just 1% monthly. Let's change it to 1.01 factor. No, that's not correct. What I want to do is take v, that equals 1,000, times 1.12 is what I will end up with after t equals 1 year, 1.12 times 1,000. I need to adjust my exponent such that after 12 months, m equals 12 would be the equivalent exponent of 1. Well, what's that going to be? That's going to be m divided by 12. So when m equals 12, we'll be at 1 year, and my exponent will be 12 over 12, or 1. The same thing as this would be when t equals 1. So these would be equivalent exponential functions on an annual and a monthly basis. So be comfortable changing around the time periods that you're compounding at. Questions on the exam frequently ask you to do that. In addition, I caution you to be very careful about your common multiplier r in relation to the exponent. What do I mean by that? Well, in most cases, students look at an r greater than 1, and they immediately think it's a growth function. Y equals 100 times 2 to the x. That denotes a doubling each period. It's going to be a growth function that would look like that. If r is less than 1, students are automatically trained to think it's a decay function. For example, y equals 100 times a half to the x. The value that we multiply each period is a half, so we start at a value and we decay downward by a half each period, and the curve would look like that. Okay, that's all well and good in our normal case, but what if we have the following setup? Y equals 2 to the x and y equals 2 to the negative x. In both cases, the common multiplier r equals 2. But are these in fact both growth functions? I don't think so. Y equals 2 to the x. Well, that is going to be our regular growth function. We're going to double each period for y. What about y equals 2 to the negative x? Well, I'm going to manipulate my exponents with my exponent laws here just a little bit to recast this as y equals 2 to the negative 1 raised to the x power. I can do that under my exponent laws. What is 2 to the negative 1? Y equals 1 over 2 to the 1, or 1/2 to the x. Whoops, with that negative exponent, my r equals 2 really became an r equals 1/2. This became a decay function, or it really was from the get-go a decay function. You just had to be careful about the negative exponent. So these two were fundamentally different. One was, in fact, a growth function. The other was a decay function. So be cautious about the exponent in relation to your multiplier. I also caution you to be careful about a shift in the measurement periods over time. So for example, let's suppose we started with a function y equals 100, my initial amount, times the common multiplier 2. So I'm doubling every period to the number of periods where n represents the number of years from 2020. By the way, interpreting exponential functions is also going to be important, just like our linear interpretation problems in Heart of Algebra. I need to understand what the 100 and the 2 represent. A doubling each period from an initial amount of 100. Okay, so what does that look like? Well, I can kind of map that out. We'll call 2020 year 0, then 1, 2, 3, and I'm going to start with 100. I'm going to double that. That becomes 200. And I double that again. My multiplier applies every period, so that goes 2 times 200 is 400. 2 times 400 is 800. So I know I have 800 at the end of year 3, which is 2023. Suppose we define t as the number of years from 2023. The question might ask, what is the equivalent function to my original exponential, but in terms of t? What would that look like? Well, how would I go about doing that? Well, first thing I'm going to note is that the number of years from t and the number of years from n are related. If I'm in 2023, t equals 0 and n equals 3. So t equals n minus 3. And I can use this and my exponent laws to figure out my new function in terms of t. So rearranging, I know n equals t plus 3, and I can plug that into my original function to get my function in terms of t. Y equals 100 times 2 to the t plus 3 power. That would be the equivalent function. And let's just check that to be sure. What happens in year 3? Well, I get 100. Rearranging t plus 3, I know that's the same as 2 to the third times 2 to the t. When I multiply exponents to the same base, I add those exponents. Well, 2 to the third is 8, so that really becomes 800 times 2 to the t power. And what is t in year 3? Well, in year 3, t is just becoming 0, because that's 2023. So that would be 800 times 2 to the 0 as a check. And that, of course, is 1. The answer is 800. This function, expressed as t, gives us the very same value we would expect to get in year 3, or number of years from 2023, 800. They are the same function. The second one just expresses it in terms of t. So get to know how to make those adjustments and manipulate your exponent laws. So as we finish up our exponential functions, I might point out it is essential to know your exponent laws inside and out and be very good at manipulating them. Okay, let's move on to our last topic in advanced math topics, rational expressions. Finally, we're going to learn how to divide polynomials. Rational, if we recall what that word means, it's essentially the same as a fraction. A rational number is a fraction of integers. A rational exponent in our exponent laws is an exponent that's a fraction. So rational expressions, it's essentially one polynomial f of x divided by another polynomial g of x. So how do we go about doing that? What would that look like and how will we solve? Well, if we're lucky, one approach is to factor and simplify. So let's suppose f of x were x squared plus 5x plus 6, and g of x were x plus 3. Well, I might try to factor x squared plus 5x plus 6 if I can, quickly. And I note it's x plus 3 times x plus 2 divided by x plus 3. I can cancel and simplify. The function value becomes x plus 2. That's what the division of f of x divided by g of x is in this case. And of course, x cannot be negative 3. That's not part of my domain. If x were negative 3, then minus 3 plus 3 would be 0. I'd be dividing by 0, which is undefined. Usually, we're not that lucky on the exam. What we typically have to resort to is learning polynomial long division or synthetic division. I'm not going to focus on teaching both methods here. They're essentially the same. I'm going to teach you polynomial long division because it works and it's simple. Synthetic might be faster and easier for many of you in a lot of cases. Feel free to use it. So how is that going to work? Let's start with this same example. By the way, notice in that example, x plus 3 divided evenly into the f of x, x squared plus 5x plus 6. That's kind of analogous to 3 dividing evenly into 9, and you have no remainder. If it were, for example, x plus 1 dividing into the top polynomial, x squared plus 5x plus 6, we would get some remainder. Just like when we divide 2 into 9, we get 4 remainder 1, or 4 and 1/9. Same analogous idea occurs even with polynomials. So how do I actually do my polynomial long division? I'm going to set it up much like I would division on regular numbers. I'll have x plus 3, what I'm dividing into, the number I'm dividing into my division symbol. In numbers, what I try to do is find those numbers that multiply out to the powers of 10 inside my division symbol, starting with the largest powers of 10, working downward until I'm finished or have only a remainder left. Same idea here, but instead of highest powers of 10, I start by eliminating the highest powers of x's that I possibly can. So how would I go about doing that in this case? Well, I need to multiply something by x to give me my x squared. That way I eliminate, when I subtract that second row in my division, the highest exponent of the x squared. So what is that going to be in this case? Well, if I multiplied x by my x, I will get x squared. And I know that's going to match out and cancel out. Okay, well, I'm not done. I still have to multiply the x by the other parts of the divisor, 3. X times 3 is plus 3x, and there's nothing left there. So now, like in regular long division, I'm going to subtract my second row from the row above. X squared minus x squared cancels out. 5x minus 3x leaves me 2x, and 6 minus, there's nothing there, is 0, is plus 6. So now I have my next line in my division. I have to move down 1 degree in x and do the same process. What do I multiply here? What number in this case do I multiply by x to get 2x and cancel it out? That's going to be plus 2. 2 times x gives me 2x. And I still have to multiply the 2 by the plus 3. So 2 times plus 3 gives me plus 6. And now I'm going to subtract that second row from the first. 2x minus 2x cancels. 6 minus 6 cancels. I have 0 remainder. I knew that already because I know x plus 3 is a factor of my polynomial and divides evenly into it. The result of that long division is x plus 2. And we know that's the case because we know x plus 2 times x plus 3 are the factors of x squared plus 5x plus 6. So that's how we would do our polynomial long division. Let's look at another example where we have a remainder and our divisor does not divide evenly into the numerator polynomial. FYI, you don't typically have to graph rational functions for the exam, which is kind of nice, but you might note that the roots of a rational expression are the same as the roots of the numerator polynomial. Who knows? That might come in handy at some point. Let's go ahead and try this example. X minus 3 divides into 2x squared minus 5x minus 1. And I'm going to multiply the x by 2x. And I like to keep it over the same x's and x squared columns, whatever the degree of the particular variable is, to keep things organized. Just like in long division, I keep the hundreds over hundreds, tens over tens, etc. So 2x times x gives me 2x squared. 2x times minus 3 gives me minus 6x. And now I'm going to subtract that second row. 2x squared minus 2x squared cancels. Minus 5x minus 6x, be careful of your signs, is plus 6x, which ends up being plus x. And then minus 1 minus 0 is minus 1. Okay, what can I multiply now? What number times x can I multiply to match up to my x? Well, that's just going to be plus 1. So 1 times x is x. 1 times negative 3 is negative 3. And again, I'm going to subtract that second row from the first. So x minus x is nothing, 0. Minus 1 minus minus 3 becomes plus 2. So x minus 3 divides into p of x, giving us 2x plus 1 plus a remainder of 2. And that remainder of 2 gets expressed as a fraction over the divisor. That is over x minus 3 in the denominator. Just like if I divided 9 by 2, I could write that as 4 remainder 1, or in fraction form, 4 and 1/9. This is exactly analogous to what I'm doing up here. And that would be the answer of the long division. Okay, let's practice another example just to make sure we're good at our execution. So, for example, what if I had x to the 6th plus 2x to the 4th plus 6x minus 9 divided by x cubed plus 3? The important thing to note in this case is that I have gaps in my exponents. I've gone down one by one by one in order in the previous examples, not here. So what if I have x cubed plus 3, and I'm going to divide that into my numerator polynomial. I'm not just going to write x to the 6th and then my 2x to the 4th. I'm actually going to add a 0 x to the 5th column, then my 2x to the 4th column, and then a 0 x cubed column plus a 0 x squared column, plus then my 6x minus 9. Why did I do that? Because keeping my columns in order and working through every column by column will keep me organized and doing the right subtractions as I go along. Otherwise, I'm definitely going to confuse and mix up my columns. So execution-wise, this is a good tip to follow. Okay, so what do I need to multiply x cubed by to get my x sixth? I'm going to multiply by x cubed, 1x cubed in that column. The x cubed times x cubed is x to the 6th. My x cubed times 3 is 3x cubed. Well, that's important because remember, if I didn't separate it out, I wouldn't write my 3x squared in the right column with 0x cubed. Now I can go about my subtraction correctly. These cancel. I get 0x to the 5th. 2x to the 4th minus 0 is 2x to the 4th. 0x cubed minus 3x cubed is minus 3x cubed. 0x squared is 0x squared. Plus 6x minus 0 is plus 6x. And minus 9 minus 0 is minus 9. Now I'm going to go through the same type of process. What can I multiply by x cubed to give me 2x to the 4th? Well, that's going to be 2x in this case. 2x times x cubed will give me 2x to the 4th. And then 2x times 3 should give me plus 6x. So there's nothing in the cubed column, there's nothing in the squared column. I'll get plus 6x in that case. And as I subtract, well, those cancel nicely. Even the 6x's cancel nicely. I'll get minus 3x cubed plus 0x squared minus plus 0x at that point minus 9. Okay, what now do I multiply x cubed by to get my minus 3x cubed? Well, nothing by x because they're already the same power, so that's going to be a 0 there. And I'm going to multiply by minus 3 in the digits column. Minus 3 times x cubed gives me my minus 3x cubed. And minus 3 times 3, it gives me my minus 9. That exactly matches the row above it. There's no remainder. This divides evenly. X cubed plus 3 divides evenly into this long, ugly polynomial, leaving me x cubed plus 2x minus 3. These are essentially the two factors of my original numerator polynomial, if you want to think of it that way as well. So this execution detail of breaking out and lining up skipped columns when you realize there's no fifth exponent, there's no third, there's no squared term in your numerator polynomial. You want to set them up in the long division. Okay, now let's look at what might be an ugly and challenging case at first appearance. So you've got this long polynomial in the numerator with two variables. How would I go about this? Well, I'm going to follow the same process. I've got to match my x squared by multiplying something by x. Well, what's that going to be? I'm going to multiply x. That gives me x squared, and x times y gives me plus xy in that column. Now I'm going to subtract. X squareds cancel. I end up with 2x squared y minus 2 minus 1 is minus 3xy. I'm subtracting that second row, and everything else pretty much just falls down into place. Now I want to find something I multiply by x to get rid of my 2x squared y. What's that going to be? A little more tricky, but it's going to be an xy. It's going to be p plus 2xy. Multiply that by x, and I'll get 2x squared y to cancel out that leading term. I still have to multiply that by y, so I get 2xy squared. Well, that's going to be 2xy squared. Fortunately, when I subtract that second row from the first, that cancels, and that cancels nicely, just leaving me minus 3xy. The minus 3y squared drops down. And my last, hopefully last step, will be what do I multiply my x by to match up to my minus 3xy? Well, that's going to be minus 3 times y. So minus 3y gives me minus 3xy. And then minus 3y times plus y gives me minus 3y squared. That also cancels nicely, and I end up with no remainder. So another really useful theorem, a third approach to doing our division of polynomials, is the remainder theorem, or when there's no remainder, we call it the factor theorem. This is a really good technique that answers a lot of questions on the SAT for long division, saving us the effort of the synthetic or the long division. So what does the remainder theorem say? It says if I have a polynomial p of x in my numerator, and I divide by a linear, that is a degree 1 polynomial of a form x minus c, where c is the constant, then I could plug that c back into my numerator polynomial, my numerator function, and the result will be the remainder for that function. All right, let's try that in practice. My numerator p of x is 2x squared minus 5x minus 1. My denominator polynomial is the binomial x minus 5. So in this case, c equals 5. I plug in p of 5, which above is going to be 2 times 5 squared minus 5x, so that's minus 5 times 5 minus 1. What do we get as a result? 5 squared is 25 times 2 is 50. Minus 5 times 5 is minus 25 minus 1. The result is 24. My remainder for this division is going to be 24. Now, I might not know what all the other terms that divide evenly into p of x are beforehand, but if it's multiple choice and there's only one answer that has that last term, dot, 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 plus 24 over x minus 5, guess what? I know this has to be the correct answer. So I avoid the entire long division. I just take advantage of knowing how to quickly calculate the remainder. I can also use this same theorem to find out if my denominator polynomial is a factor of the p of x, of my numerator polynomial, very quickly without any full long division. So in this case, I have p of x is x squared minus 3x minus 4. X minus c is x minus 4. So that means c here equals 4. I'm going to plug c back into my numerator polynomial for x. So I'm plugging in 4. 4 squared minus 3 times 4 minus 4. What does that equal? That equals 16 minus 12 minus 4, which is 0. I have 0 remainder. Right away, I know x minus 4 is a factor of x squared minus 3x minus 4. What if instead I had x squared minus 3x minus 4 divided by 3x minus 2? How do I work with that? Is 3x minus 2 the same thing as x minus c? Well, essentially for our purposes, it is. It's a linear polynomial. But how do I calculate c? What is c in this case? Well, c, I could figure that out by essentially saying 3x minus 2 equals 0. X equals 2/3. That is going to be my c value. So now, in this case, my C equals 2/3, and that's what I want to plug back into my numerator functions. I'm going to get minus 50 divided by 9. And we can deal with these presentations and calculate C and use our remainder theorem.